As we continue on with our counting problems, and strings in particular, we'll look at this next problem. How many bit strings of length n are there? And secondly, how many of these start and end with a 1? So recall that a bit string is a string of zeros and ones. So this is something like 0, 0, 0, 1, 0, 1, 1, 0, 1, something like that, a bit string. But it has length n. So if it's a bit string of length n, then what we're going to do is form this in a sequence of steps, in fact n steps. And in each step here, what we're going to put is the number of choices. And that would be from 0 or 1. So there's always 2 choices for each bit in the string. And taking the product of those, because they are steps forming the 1-bit string, the whole bit string that we want. So we're taking the product of those, we'll get 2 to the n such bit strings. Now you might think for a minute, okay, pause it, and think about how many of these start and end with a 1. Okay, so how are we going to get those that start with an end with a 1? Well, in the first place, it has to be a 1, so there's only one choice. It happens to be that the choice is 1, but there's one choice. The second one can be anything, the third one, etc. Out to the very last one, the nth one, because it starts and ends with a 1, there's only one choice for that one as well. That's 2 to the n minus 2, right? That's what we have right there, because there's n minus 2 2's and 2 1 factors right there. So let's leave this idea of bit strings and talk about the notion of a set. And it's likely you've seen sets before, but possibly not. The term set, that as we'll use it, is a collection of objects. The objects can be anything. It does not involve order. It's just a collection of things. And the notation that we'll use, typically we'll use these braces for the set. So it's like the braces or the box, and the things in the set, in this case up here, are B, C, D, and F. So that set has elements B, C, D, and F, or members we'll sometimes say. Now that's the same as this set here. I just happen to list the things differently, but it's obviously the same things that are in that set. And in fact, it's the same as this set here. It's just like I said, well, in this set we have C and F and C and F and D and B. It's redundant, simply calling out the things in the set more than once. So those three are all the same set. What specifies a set is what's in it. What are the objects in it? Not however many times you might say it or the order in which you might list them. The order is immaterial. I'll use this notation here. Let me get rid of that for a second. I'll use this brace, or this notation, looks like absolute values, to mean the number of things in a set. So in our example of the set whose elements are B, C, D, and F, then we have that the number of things in the set is 4. The union of two sets, the union, the symbol here for union, U here should call to mind the nature of the symbol itself. The union is the join of the sets, putting them together. So it consists of all the objects that lie in at least one of the two sets. So if we take the set A, as I've described it there, with elements B, C, D, and F, and the set B with elements D, F, G, and H, then the union, look and see what elements are in either of the two sets or both. And in alpha order, it's B, C, D, F, G, H. That's the union. Whereas the intersection, which uses this other symbol here, will be the things that lie in both or all of the sets if there's more than two. And the things that lie in both of them simultaneously are just D and F in this case right here. So that's the intersection. That's the overlap where they meet. Or the meet. And the union up here is the join. You join the sets. Those are terms some people use, but union and intersection are the most common. So the sum rule, which is really the most natural of the rules, but we'll state it because sometimes it's we need to use it in a particular way. The sum rule says if you have a set of objects, so a bunch of things, and you can split them into two sets that have no overlap, no things in common, so you've just subdivided it or partitioned it, then the number of things in the whole set, which is the same as the number in the union of the two that split it, is the sum of the number in the first set B plus the number in the second set C. That's very natural, very simple, very straightforward. So let's see if we have time to squeeze this in here. We might have a passcode that consists of a string of either 2 or 3 case-sensitive English letters followed by 3 digits. How many different possible passcodes are there? And I think the best way to do this is to notice that because we have this 2 or 3, we're best served by saying those that start with 2 digits will have 2 English letters, first letter and the second letter, and then the digits, 1, 2, 3 digits. And there are 52 choices for case-sensitive English letters, and then 10 choices for each of the digits. So this would be 52 squared times 1,000. That's those that have 2 letters that lead in, and those that have 3 letters that lead in, 52 times 52 times 52, like so, the first, second, and third. Third, I'll write it up here for space, and they still follow by 3 digits, so that'd be 52 cubed times 1,000. Now each of these represents a number of ways to get a passcode. They're distinct, that is non-overlapping ways to get passcodes, totally different passcodes, so the total is just the sum. 52 squared times 10 cubed plus 52 cubed times 10 cubed. Right? So the plus there is significant right there. Okay? We'll stop there.